Hello, and welcome to Machine Learning Development and Concepts. The goal of this is to simulate a technical interview focused on the practical process of building and validating machine learning models. Along the way, I'll be articulating the systematic steps of the ML project, including the definition of key concepts and a problem-solving skills demonstration using the STAR method. The three prompts will be: 1. Describe the key steps in the machine learning and development lifecycle. 2. What is feature engineering and why is it important? And 3. Explain the concept of overfitting and underfitting and provide an example of a time I resolved one of the issues using the STAR method. I'll try to keep it to under 7 minutes. I haven't been very good about it. The machine learning development cycle, also known as ML, is a process used to build, deploy, and maintain robust machine learning models, typically involving the following steps. Number one, problem definition and problem scoping. That is clearly defining what the business problem is and the goal of the ML solution, as well as the metrics, that is the accuracy, recall, business impact, that will measure what success is essentially. Data acquisition, number two, and ingestion. That is identifying and gathering the necessary data for various sources, databases, APIs, logos, and ensuring the data is legally and ethically sourced. Number three, you'll want to know number two before you get started, right? Because you might run into massive hurdles. Number three is data cleaning and pre-processing. That is often the most time-consuming step as it involves handling missing values, correcting inconsistent data and formats, and identifying and managing outliers and performing tasks like normalization and scaling. Number four is feature engineering and selection. That is creating new features from existing ones to improve model performances and to reduce dimensionality and noise by choosing the most relevant features. Number five is model training and evaluation. That is selecting an appropriate algorithm and training the model on the prepared data, evaluating its performance using a separate validation, or testing the set using predefined metrics. Number six is hyperparameter tuning. That's optimizing the model's performance by adjusting its hyperparameters, parameters not learned from the data set, such as the learning rate or tree depth, and using techniques like grid or random search. And number seven is the deployment of the model, integrating the final validated model into a production environment, such as a web service or API, as opposed to one's terminal where you're running it, so that it can make real-time predictions or classifications. And of course, as you guessed it, the final step, monitoring and maintenance. Continuing, you know about that. I'm not going to go into that one. Prompt number two. Prompt number two. What is feature engineering and why is it important? Feature engineering is the process of using domain knowledge to transform raw data into input features that better represent the underlying problem to predictive models, thereby improving model accuracy or unseen data. It involves creating, modifying, or transforming and combining existing variables. Um, an example of that is extracting the month, day, and hour from a timestamp column, or creating a ratio of two existing numeric features. I recently did a project where it converted or modified the existing data, which was the year a house was made, and created a new feature for the actual age of the house to make predictions, and then added those as the X value, and the Y value was the price of the house. Why is that important? It improves the model performance. A well-engineered feature can allow a simple model to perform better than a complex model on raw data. It captures the true signal in the data. It also increases the interpretability. Creating features that are directly relevant to the problem can make the model's decisions easier to understand and explain. As I just explained in the example to you. Prompt number 3 regards to overfitting and underfitting and the star example. These two concepts describe the common pitfalls in model training that result from poor generalization. And I know this graph has been in your face along with some other stuff that I hope you've been enjoying. Um, the line in each example represents the truth, shall we say, and the circles are the different data variables. So ideally, if it was optimally fitted, you would have, as you can see in the example, a somewhat of a curve as is likely in the results of the data you're trying to get or to analyze anyway. In the underfitting model, there are some inconsistencies, and we'll start there. That occurs when a model is too simple or the features are not rich enough to capture the underlying patterns in the training data. A remedy to that would be using a more complex model, such as switching from linear regression to a neural network. Overfitting occurs when the model is too complex and has learned the noise and specific details of the training data too well. I am not the biggest fan of this diagram just because I think it would be easier if there were only one form of data. For example, when I was talking about the x values earlier being, or the x value being a combination of the age of the house and of the actual year of the house, and the y being the price range, if the model predicted it in a very well fit together model, the data points would be close to that line, and in one that's not so well together, it'd be farther away. Um, you might think it's overfitting if it tries to be too many things to too many data points, uh, if you will. For example, if it's analyzing, columns that have data that aren't really relevant, but it hasn't been caught yet, so it's important to keep an eye on things like that. Using the star method, um, I built a random forest model for customer churn prediction. The model was severely overfitted, and I was able to achieve 98% accuracy on the training data, but only 65% on the test data. The goal was to generalize the model and raise test accuracy to at least 85% to make it reliable for production use. I used model simplification techniques. I reduced the tree depth. I turned the random forest hyperparameters, specifically those containing the max depth, and I increased the minimum samples of the leaf, which forced the individual decision of trees to be shallower and less detailed. Um, I also cross-validated in that I switched to a 5-fold cross-validation approach to ensure the model's performance was stable across different data subsets, further guarding against memorization. And the actions were that it resolved the issue. The training accuracy dropped to 88%, and the test accuracy rose to a reliable 86%. This generalization model was deployed and successfully helped reduce customer churn um, by 15% in the targeted high-risk group. Thank you for watching. Goodbye.